Hey y'all, we're going to continue our journey in chemistry. So for academic chemistry, this is Unit 1, Matter and Measurement. We are going through Skill 2, Classify Matter. This is the second installment of these notes. So today we're going to talk about mixtures. And mixtures are the type of matter that you're probably most familiar with, because usually you're not coming into contact with like a big sample of one specific element or one specific compound. So first let's define it. Mixtures are made of two or more pure substances in the same space, but they're not chemically bound together. So for example, if you look at this picture at the atomic level, or the particulate level, see how I have this black, red, right? That's one piece and it's chemically bonded to itself. Versus over here, I've got something with blue that you don't see in this piece. So that means that they are different, but they're in the same vicinity. They're not chemically bonded, so as in they're not touching in this representation, so I know that they're not chemically bonded together. So jelly beans are a pretty clear example of a mixture, right? You know that you have a whole bunch of different flavors, which means there's different compounds that make those different flavors that when they go in your mouth, you sense those different flavors. Coca-Cola is a mixture. If anyone ever becomes like a food scientist or an engineer that works in the food industry, you'll know that there's certain components that go into foods to make them. And particularly when you're going in industry, you'll have a range of, okay, you can put from this to this many grams of sugar in each batch of soda and it'll be fine. No one will even tell the difference. So every single batch of Coca-Cola that comes out is actually going to be a little different, but there's that range that your taste buds can't tell the difference. So the industries know what that range is, so they don't specify their instruments calibrating to that point because they don't need to. So every single batch of Coca-Cola is slightly different than one before. And then Ralphie is a mixture. Not every part of Ralphie is the same, but there are obviously pure substances that make him up because pure substances make up everything, because at the basis, everything's made up of elements. But if you look at Ralphie, your little smushy face, not everything about him is the same, right? His hair is different from his eyeballs, which is different from his nose. And then we also have in chemistry solutions, and we'll go over that a little bit, but those are always mixtures because they're made up of different things inside. So basically most matter is going to be considered a mixture. Like I said at the beginning, it's really rare to ever find something that's a true pure compound. Mixtures can always be separated by a physical change. So there's no change to the chemical composition of the matter, but you're able to bring things apart. And this is all based on their physical properties. So boiling point, if it's one thing's magnetic, another thing isn't. You could have physical separation, like that thing of Skittles, right? You could definitely tell which ones are blue and which ones are red, and you could just literally pick them apart. There's obviously no chemical change when you do that, but you did just make a change. So let's go over the differences between mixtures and compounds. So in the notes, this is going to be set up left and right, just like you have in this PowerPoint. Notice if I have two elements here, X and Y, when I have a mixture of them, those elements are still hanging out by each other. But over here, I have compounds of them. So let's go over what makes each. So first, a mixture. When elements come together to form a mixture, first things first, they retain all of their properties. So if I put something of, sulfur in with another element, that sulfur is still going to be yellow, it's still going to smell bad, it's still going to be flaky, it's still going to be a solid at room temperature. They can be separated by physical means. So if two things come together to make a mixture, I can take those two things apart without damaging either of those two things or without altering either of those two things. And this is the big key point that students really need to know. If two things come together, or more, it could be more than two things, but if pure substances come together to make a mixture, then the samples do not all have the same exact composition. So like I said earlier, the Coca-Cola that you drink, right? Not every single bottle of Coca-Cola is exactly the same. There's that range of how much sugar they can put in. There's the range of how much syrup they're going to put in each one. So since it's not exactly the same ratio of ingredients, then that's part of what makes it a mixture. So here's another example at the atomic level. So this is going to be hydrogen and oxygen. Sorry, these are the hydrogen, this is the oxygen. And when they're around each other, they're still just hydrogen and oxygen. But what if I made something into a compound? So when elements come together to make a compound, first they obtain new properties. So if I put sulfur into a compound, it's not necessarily going to be yellow. It's not necessarily going to be smelly. It's not even necessarily going to be a solid anymore. Like sulfur dioxide is a gas because sulfur is now bound to oxygen and they have all new properties. It's going to require a chemical change to separate them, and we'll go over later in the course what exactly a chemical change is, like what signs you can look for, but essentially you've changed their chemical composition. And the last thing that's really key about compounds is all samples are chemically identical. So whereas the Coca-Cola, not all of them are exactly identical, if you have a sample of water, H2O, it doesn't matter where you get it, it's all going to be H2O. It'll always be 2 hydrogens for every 1 oxygen. No matter what sample you get it from, it's exactly the same. And that's what makes it a compound. That's one of the characteristics that makes it a compound. So let's go over a few ways to separate mixtures into their pure substances. So the first is something called chromatography. Now, chroma, it comes from color, but it's not always going to be related to color, but we are able to see the exact place where these mixtures separate. So chromatography allows mixtures to pass through a solution, and each pure substances will stop or be slowed at different points along the solution based on its properties. So here's a little picture, and this is going to be a size exchange chromatography. So you see how you have a mixture up here of green and pink, maybe red atoms. And the green are obviously much bigger, and this could be molecules, this could be atoms. I don't know what the sample is showing us, but you'll see that the green just like falls straight through. So we're letting gravity pull it through, but the red ones get caught up in these pieces up here. So then the green's going to be spat out first, and the red's going to come out later. So you can separate things in chromatography based on their charge, based on their size, based on their polarity, which means just like how the molecule, the charges in the molecule are oriented. So there's a whole bunch of different types of chromatography, and if you study science in college, you're going to do a lot of really cool labs of chromatography. Some of you guys might have even done a chromatography lab if you've separated ink before. That's a really common one that they do in schools. It's really cool. Next is filtration. If you've done any cooking, and made some pasta, you have done this. So in science, we're going to have a filter paper generally to do this, and that's going to just let the liquid go through and particles get trapped. So this is going to separate a liquid from a solid by allowing the liquid to go through a filter paper and blocking the solid. One of the things to note about this is the solid has to be large enough to not travel with the liquid. So if you put something like salt in with a liquid, that salt is actually going to dissolve into a water, and that would travel with. But if it's something larger, it's going to get trapped. You'll also, if you talk about like the gold rush and when people were shaking those little dishes to try and separate gold from the water out in California, there's lots of pictures of that. Like that is a type of filtration. If you make pasta and you're separating the pasta from the water with a colander, then that's going to be filtration. In the lab, we generally using smaller things, so we're going to need a filter paper to actually separate even smaller, stop smaller things than what you would use outside. Next is distillation, and you might have heard of that. There are a lot of things out there that you can buy that are distilled. So distillation, here is a distillation apparatus, which looks crazy. If you take organic chemistry, you will build this just about every single time that you have a lab, and it looks a lot crazier than it is. It's actually really simple. So it separates 2 liquids that have different boiling points. So the liquid, the lower boiling point evaporates first when heated and moves to the receiving flask. So if I have 2 liquids in here, as I start to boil, it's only going to heat until it gets to whatever the first liquid's boiling point is. And then that liquid's going to boil, come up, and then since it's cooler down here, so This has cooling based on water. A lot of times you'll just put an ice bath under here. So since this is cool, it's going to actually attract that vapor, and it's going to come here and it's going to condense as soon as, so it'll end up dripping down here. And then you've got the one with the higher boiling point here and the lower boiling point over here. So here's two liquids, and then the lower boiling point ends up over here. Next is evaporation, something you're very familiar with when you learned about changing between solids, liquids, and gases back in the day. But we can speed it up in the lab by literally boiling something off. So if you have a solid that's dissolved into your liquid, then you can boil off the liquid. So it separates a liquid from a substance that is dissolved in. You're typically not seeing that substance anymore as its own particle. Sometimes it'll make the liquid murky, or sometimes it'll take over the color of the water because that color is so bold. So like if you have a copper sulfate solution, it's going to be copper sulfate in water, but it actually turns the whole thing blue because of the copper sulfate. The substance will be a solid once the liquid is gone. So that substance is going to be left over at the bottom of your dish. And this can be done by sitting out and naturally evaporating, or if you want to speed it along, you can heat it to a boil. You could put it in an oven, but typically we're going to put it on either a hot plate or you're going to put it on top of a Bunsen burner for a direct heat source. So there's two different types of mixtures. The first is I'd say homogeneous, but I hear other chemistry teachers say homogeneous, which might be what you've heard. I like saying homogeneous because that's how I learned it, and it also helps me identify that prefix. So the prefix homo means the same. So when you guys were in biology, you probably learned the phrase homozygous, which is when you have two alleles that are the same in genetics. So homogeneous mixture is a mixture that is a mixture. See how this has different particles throughout it? But they're all almost evenly spread around. There's no distinction between where those particles are. Versus a heterogeneous. So hetero means different. So heterozygous, when you did biology, was when you had two different alleles from mom and dad. Maybe you had like a brown hair and a blonde hair allele, and then the brown hair expressed itself even though the blonde hair was there, right? Sound familiar? So a heterogeneous mixture, it's still a mixture because you have different particles, but you notice these particles here all look the same versus these particles here look the same. So there's two different phases or two different states, at least two. There could be three, there could be four. So homogeneous mixtures look the same throughout from the macroscopic view. So if you're looking at it, then it looks the same throughout. So like the air around you all looks the same. So that's homogeneous or homogeneous. Heterogeneous mixtures look different throughout because they have two or more phases. So like, if you look at me, I'm a heterogeneous mixture, right? Like if you had a sample of my hair, that's not going to be the same as a sample of my fingernail, which is super creepy. So don't ever take someone's hair or fingernail and claim it's for chemistry. All right, so let's do some homogeneous mixture examples. So milk would be a homogeneous mixture. So it looks the same throughout, but it's got a whole bunch of different stuff in it. It's got lipids or fats. It's got proteins, it's got ions in it, it's got water in it, so it's got a bunch of stuff in it, but even though it's got a bunch of stuff, if you look all the way through, it looks the same. Steel, a lot of people forget that steel can come in different varieties, so like stainless steel is a type of steel, but even within that, different stainless steels are going to have different compositions, so that's why you know it's a mixture. It's not a compound because not all steel is made the same, and even not all stainless steel is exactly the same. But when you look throughout it, it looks the same as far as that piece of steel, so that's going to be homogeneous. And then anything that says the word solution. So in chemistry, you're going to see a lot of things of like, oh, get that 3 molar copper sulfate solution. So what solution means is you took a solid, generally a solid, and you mixed it in. It's often going to be within water if it's a polar substance, and then you literally mixed it up. So you mix those two things, you know it's a mixture, but it looks the same. See how these all look the same throughout? That's why they're homogeneous. And then let's go over some heterogeneous mixtures. So oil and water. they don't mix together. So they're going to stay separated. If you've ever looked at salad dressing, you'll know that they don't stay together. I also have a pretty cool salad dressing dispenser in the room. If you ever want to check that out, ask me about it. It keeps them in different compartments. You can pour separately. It's pretty neat. Pizza is going to be a heterogeneous mixture, right? The crust is not the same as the cheese. And even though the things that make it up themselves might be homogeneous mixtures, like the cheese is a homogeneous mixture, when it comes together with everything else, all the pieces together make up the pizza, and now you have a heterogeneous mixture. So it looks different throughout. There's different phases. There's different pieces of it that are different. Anything that's living is actually a heterogeneous mixture. And a lot of students struggle with this, but if you think about it at the atomic level, a little bit bigger than the atomic level, then you've got cells, and the cells aren't going to be the same. Plus, if you think of me, like I've got my blood flowing in me, right? And I said earlier, the skin, the nails, everything's different about me. But even if you have like a little bit teeny tiny bacteria, it might have a flagellum, that little thing that looks like a tail that helps it go. It's got a nucleus. So it's got all sorts of different stuff in it. And if you put it in a centrifuge, it'll all separate based on its size without changing any of its chemical composition. So that makes it a mixture. And because they're all different and all in different spaces, it makes it a heterogeneous mixture. So this is something that you have in your notes to kind of help you go through a stepwise process to see what's what. In the next set of notes, we're going to actually go through questions to ask yourself so you can identify what type of matter each substance is. So there are 4 types of matter we have learned about: elements, compounds, homogeneous mixtures, heterogeneous mixtures. In the next set of notes, we're going to go over some questions to be able to identify. You should already be getting an idea of what's what, but we'll go over those steps later. All right, be sure to ask me any questions if you have any. Otherwise, I'll see you in the next video.